Welcome back. So, in the previous lecture we discussed mainly on the with large scale structures also, as well as what we will see if we are having flat ramp structures or the flat ramp in the compressional tectonic environment, and what type of deformation mainly we will see on the surface. That is, we were talking about the fault bend folding or fault propagation folding. Now, if you are looking at the compressional tectonic environment and folding in particular, then you will come across the secondary faulting also. So, what we see in terms of the secondary faulting, and also in this lecture we will try to look at that if you have the change in the depth of the fault in the compressional tectonic environment, then what type of deformation will be seen, or the manifestation of that deformation on the surface. So, secondary faulting associated with thrust faulting events, mainly secondary faulting and other features are seen commonly associated with bending moment fault, flexure-slip fault, what we see here. So, you have the bending moment fault, and on the surface you see the fractures which are developed, and they will also show some displacement. So, this is on the crust of the folded material. So, we see an extensional faults here, and bending moment faults are usually related to the reverse faulting, where the bending along the fault plane result into the formation of fault on the surface. So, this is untypical of that one. Another example from these are the two examples which I am showing from 2001 Bhuj earthquake, and of course, this was not related to the co-seismic rupture, but of course, to understand that what will happen in actual co-seismic deformation, then we can take these two examples to understand the deformation. Now, example best which came up was from the 1918 earthquake of Al Asnan and 1978 Tabash-e Golshan earthquake from Iran. So, these are the two earthquakes from Iran and Algeria, which has given us an idea that how deformation changes if one there is a change in the strike, then second one is the depth of the fault. Okay. So, if you have the change in the strike or depth, then you will have a different pattern of deformation which is seen on the surface. Now, these faults are usually short and projected to shallow depth. So, this basically we are talking about the secondary faults. Okay. So, they will not penetrate deep into the crust, but if we are not able to expose the main fault in trenches, then to some extent we can also use the secondary faults to understand the pattern of deformation, or we can use this to reconstruct the history of paleo earthquakes. So, this is an example of the trench which was excavated after the 1980 Al Asnan earthquake from Algeria, which shows the topography which was developed on the surface because of the faulting or the deformation, but the fault did not reach right up to the surface. So, what has been taken into consideration, the secondary faults which were developed along the folding, and this helped in identifying the different earthquakes in that region. So, you can also have the normal faults which will develop on the surface because of the folding. So, flexure-slip faults, formation of flexures on the surface related to faulting. So this basically we consider this as a secondary deformation, and they are formed due to sudden bending of thick layered sequence. Such faults are accompanied by slip along bending planes in fold limbs during the deformation and are rooted in the axis of the fault and extend through the fold limbs, but they will not be deep seated. Okay. Whereas this fault cuts the surface, they produce scarps, as we were looking in the previous slide. So they will produce the scarp, and such features mimic those features produced by tectonic surface faulting. So need to be very careful in understanding whether they are secondary, related to the secondary deformation, or they are related to the co-seismic. So the secondary faults developed over the fracture or fold formed due to bending moment or flexure-slip are not considered as seismogenic faults. Okay. However, the fault causing the flexure or warping on the surface is seismogenic. So what it says is that you have the folding which is taking place, or warping or flexuring is your co-seismic or seismogenic, but the displacement which you see on this flexures are because of the bending moment or the flexure slip, and they are not seismogenic, but the folding which has occurred is seismogenic, as we were looking in the previous slide from the trench log of Alasnam earthquake. So again, coming back to the portion from Kutch region, so what we saw is that we have the slip which has occurred along the so you have the ramp here, and then you have flat here. So you see the folding on the top, and on the surface we were able to see some fractures or the displacement which was been observed, and you can see one is over here, and along with that you will also have the back thrusting. Okay. So you have the secondary faults which have developed here, but the main fault is sitting somewhere over here like this. Okay. So what we were able to fix up based on the this sketch here which has been shown. So you have the ramp here and the flat, and then you have the secondary antithetic faults, and also some displacement was been seen along the extensional part which has occurred on the crust of the fold. So deformation related to 2001 Bhuj earthquake. Again, this was the secondary one. So the upper portion of the pressure ridge. So what was developed here, a typical pressure ridge which is been seen in couple of co-seismic ruptures. So the pressure ridge, and on the surface we saw the extensional cracks. So this is what you see here, the extensional cracks were developed, and this was due to the bending moment of the bedded sequence. Okay. Now thrust fault scarps. Okay. Forms of the thrust fault scarps are more varied as compared to other fault types. Okay. And this will be due to the complex nature of low angle faulting and folding, one, then due to the complex response of the surface material, amount of slip on the fault, sense of slip, geometry of the fault. So based on this, you will see in nature that you will have different type of deformation or the surface manifestation during thrust faulting environment. Okay. So in 1992, Philip and his team have described 7 type of thrust fault scarps that were produced along the Spitek fault during 1988 in Armenia, and this is one of the best example which explains that because of this parameters, okay, the nature of low angle faulting unfolding, response of the surface material, amount of slip, sense of slip, and geometry of the fault. So if the depth changes, amount of slip changes, and depending on what material in which area the faulting is occurring, then that will result into the different type of fault scarps. Okay, so 7 type of fault scarps have been described from a single event. So let's see quickly what we are able to learn from this. Okay, so this all 7 A, B, C, D up to G were from the same faulting event, and you can easily make out that you have the different due to different material and also the geometry of the fault. You see different type of deformation on the surface. Even you will come across the faulting like what we see in the strike slip faulting environment. Okay. So this marks all the fault. So you have one going like this, another is on the surface here, there is a bending here is taking place, as well as it shows the back thrust developed, and here also you have the fault going here, and then back thrust is developed. Back thrust we are usually talking when the dip of the fault is opposite or is not in the same direction, where the main fault dip is in this direction and the dip of the back thrust is in exactly opposite direction. So this is again and very typical of fault bend folding and very high angle fault here, and then depending on the material you will see whether the extensional cracks will formed or not, and if you are having some oblique slip because of the change in the strike, then you will come across the strike slip faulting environment. So let's see one by one what it says. Okay, so one is your considering the material in the bedrock. So what it's been shown here is your bedrock here. So this deformation is has occurred in the bedrock. Then you have the soft sediment which has been seen here. So you have the bedrock here. Here is also it is shown bedrock, but what we see is the bedrock, and then you have the soft sediment. So what typically it shows is that in the bedrock the fault has remained almost with high inclination or the dip, and then as soon as it goes into the soft deposits it bends, and similarly it has been shown here. So it has a very sharp high inclination and it bends here. Okay, and third is your surface. Okay, so you have the surface here. So as soon as it comes through the surface and it becomes almost flat, or the inclination is reduced, the dip reduces. Okay, so this should be kept in mind when we are opening the trench and trying to identify the contact. So A is the simple thrust or reverse scarp. Okay, these are produced by steep dipping greater than 45 degrees reverse fault in bedrock. Okay, so in bedrock you will come across a very sharp scarp. Okay, whereas in the soft sediments you are not looking at those. Okay, so B is the hanging wall collapse scarp. Okay, so you have the displacement coming up, and then you are having the material which got collapsed. So scarp material is collapsing. So steep falls in brittle unconsolidated material where hanging wall collapse during seismic shaking, because you will have the displacement, and along with that you will have strong ground shaking that will result into the collapsing of the material here. And of course along with that, this collapsed material will also show some extensional cracks which are developed here, or the extensional faults. Okay, C is the simple pressure ridge which is produced due to low angle thrust faulting. So you have a very low angle thrust faulting which is coming here. Okay. However, development of pressure ridge depends on the material, rheology, and the magnitude of the slip also. Okay. Then D, what you have is the brittle material produce fissures in the leading edge. Okay, so you have the development of the fissures on the leading edge of the thrusted sheet, if the displacement is more, it may result into formation of secondary normal faults. Okay. So these are all secondary normal faults which have been seen. Okay. Now looking to the E part, okay. So this is an example of what we are talking about. You have a very sharp and some portion you will see the collapsed material. So this again will depend on the material. Okay. So you have the fault plane here, and then you have some collapsed material here. So reverse fault scarp produced, this was in 1971 San Fernando earthquake in California. So A, what you see is the hanging overhanging scarp with the fault plane of almost 65 degrees. Now this is what has been shown, the fault plane, the fault scarp, and then B is your collapsed material. So this is your all what you see is the collapsed material. Again, coming to the pressure ridge, which we discussed in the previous lecture. So you have the cracks which have been seen, or the displacement on the surface. Okay, and this is because of the bending. So again, the dip of the fault has played an important role. Now coming to this part, this is a trench which you open. So you can see the scarp here. This is up and this is down, and very beautiful scarp can be seen here. This is a typical thrust faulting environment from Himalaya. When we open up the trench here, so this is the back hole which has been shown here, and this was the trench site. Okay. So what we saw is very interesting, that is change in the depth has shown us the different deformation pattern, okay, on the same fault, and the trench width, if we take, was not more than 3.5 to 4 meters. So this is your, like for example, the fault runs like this. I am drawing very straight, and the trench was open across this one. So this distance was around 3.5 meters. So what we saw, let me explain you here in this photograph. So the trench wall which we saw clearly shows that there is a displacement of this layer. So you can easily pick up this layer here. There is a sandy unit and this is a sandy unit. So it goes somewhere here like this. Okay. So you have a displacement of this unit. Okay. And you have gravel over here. So this gravel sits somewhere over here. You have, and goes right up to this here. So we identified different units here. Okay. Like B has been seen here. This is B here. This one is B, and this is B here. And then we have C, which is over here. This one is C, and this one is the D, which is capping unit of the of C actually, and then we have E here. Okay. So the fault runs here along this contact here. This we can easily make out. So it goes like this over here, and then moves further up. Okay. So there is a clear displacement which we were able to observe on the east facing wall. This is the close up of this part here. So fault is high angle here, and then it gets into the low and then becomes high angle here. Okay. So again a very typical of ramp, flat, and then getting into the ramp. Okay. So I'll just remove this line so that you can easily make out that where exactly the fault goes. So this is the contact here which has been shown. Okay. Now what we observed on the other wall, before going to that, this is the sketch of this one, so you can easily compare now the units, different units. So these are the boundaries which have been shown here, the erosional contact between the gravel unit and the sand unit here, and then the fault contact which runs here, which goes right up to this one here, and then final the capping of the recent event which took place along the C, okay, has been shown here, that is E. So E is the surface, present surface we have, and then which is capping C here. So different units which we have marked here, okay, and the same units have been shown in the trench log. Okay. So this is typically of what we were talking about, the fault propagation folding. Okay. So you have the folding of is taking place along the tip of the fault, okay, typical of that, okay, which we were able to pick up from the pattern of gravel layers which got folded. So even we can see the folding here. Now as I told that on the other wall, that is the west facing wall, what we came across was a very interesting feature. So we were not able to see the displacement as it was been observed on the east facing wall, but we saw the folding. Okay. So you can see easily the folding, this layer is over here. So if I put the units here, this is your A, so which is running like this, and then the contact has been seen here. So you have then B which goes like this, it goes like that here, and then this is the contact between the C and B. So you have C unit here, and then you have the D and E. Okay. So if I put the lines here, that will make you more easier to identify. Okay. So this is your what we see the folding. Okay, and this is because of the very low angle fault which goes along this one. So this is your the fault, but on the other wall, what we were able to see was a clear-cut displacement because we were having the comparatively high angle fault here. Okay. So within the distance of even 3 meters, we were able to pick up the change in the deformation pattern. Okay. So this is what we need to keep with us as a part of the training, that if the dip changes, that is the geometry of the fault, amount of slip and the material, then you will have the change in the pattern of deformation. So with this I'll stop here, and we'll continue in the next lecture. Okay.